Hi, this is Sulaiman Sawash, and I will be presenting our paper on generating hardware and software for RISC-V architectures. So this paper is about a backend that we can see here of a framework that actually takes a single description in a dataflow language and generates software and hardware. And in addition to this, it also generates auxiliary files to facilitate full system generation with the rocket ship generator. And the aim of this paper is to generate application or domain-specific architectures with accelerators, and also generate the parallel software that will run on these architectures and interact with the accelerators. The ultimate goals are improving productivity and facilitating design space exploration of manycore architectures, which are specific for certain domains. And a little bit of background information. So Cal is a dataflow language that we use, and Chisel, which we generate, is a hardware description language based on Scala. ROC is a Rocket Custom Coprocessor interface that is used to integrate our custom hardware to Rocket cores, which are based on RISC-V. And we also generate the extension for this interface. And a rocket chip generator is an open source system on chip design generator that generates synthesizable RTL and cycle accurate emulators. And it is written in Chisel. That's why we are generating Chisel as a hardware description language. So how do we do this? Well, a quick introduction. So in character language, there are actions which are similar to functions in C, and we can tag these actions to convert them into hardware. And the tool will also generate the software code that will interact with this hardware as a custom instruction supported by RISC-V. The rest of the code will be converted into C with mapping, communication, and synchronization mechanism to support parallel execution on multiple cores. And during the hardware generation, we use handwritten and pipelined arithmetic operation blocks as a library. And we also use delay registers to actually support the pipelining. And we put these delay registers in the necessary paths, into necessary data paths. And we test and evaluate our tools with two case studies, one from radar application area and the other one is baseband processing. We execute them bare metal on the architectures. We use Xilinx FPGA for the hardware results, and we use the cycle accurate emulator for the performance results. Naturally, the performance is improved by usage of the accelerators. And when we look at the more important result, which is the comparison between handwritten hardware and generated hardware, we can see that actually the results are very similar. And if you look at the table, we will see the comparison between handwritten and generated accelerators, and the numbers are very, very close to each other. So as a conclusion, we can say that we can generate complete systems from a single language description, and this enables fast development of accelerator-rich manycore architectures, and design space exploration becomes quite easy with these tools and the RISC-V architectures, and the differences between generated and handwritten hardware is negligible. There are certain limitations with the tools, like no loop support yet, but these are feature work. Thank you for your time.